From Earth, the Sun looks like an enormous ball of fire, burning in the darkness of space. But the Sun is not burning in the way that wood, coal, or fuel burns on our planet. Ordinary fire depends on a chemical reaction involving oxygen. But the Sun does not need oxygen to produce its light and heat. Deep inside it, a far more powerful process has been operating for billions of years: nuclear fusion. The Sun began forming about 4.6 billion years ago, when a vast cloud of gas and dust started collapsing under its own gravity. Most of the material was pulled toward the center, creating a growing sphere that became hotter and denser with time. Eventually, conditions inside the core became extreme enough for hydrogen nuclei to fuse together. At that moment, a new star was born. Around it remained the material that would later form the planets, moons, asteroids, and comets of our solar system. Today, the Sun contains about 99.8% of all the mass in the solar system. Its gravity controls the movement of Earth and every other major object traveling around it. Without that gravitational force, the planets would not remain in stable orbits. They would move away into deep space. And the solar system as we know it would no longer exist. Although the Sun is often described as a giant ball of gas, most of its material is actually plasma. At extremely high temperatures, atoms lose their electrons, creating an electrically charged form of matter that responds strongly to magnetic fields. To understand how the Sun produces energy, we must travel into its deepest region, the core. The temperature there reaches about 15 million degrees Celsius, while the pressure is so intense that matter is compressed to an extraordinary density. Under normal conditions, hydrogen nuclei repel one another because they carry the same electrical charge. Inside the solar core, however, the heat and pressure force them close enough to overcome this resistance. The hydrogen nuclei fuse together through a series of reactions, eventually producing helium. During this process, a small amount of mass is converted into an enormous amount of energy. Every second, the Sun transforms roughly 4 million metric tons of mass into energy. This may sound like an unimaginable loss, but the Sun is so enormous that it has enough hydrogen to continue shining for billions of years. The energy created in the core does not travel directly into space. Before it can reach the visible surface, it must pass through several enormous layers of solar material. The first major layer is called the radiative zone. It is so hot and dense that light cannot simply travel through it in a straight line. Photons are repeatedly absorbed, released, scattered, and sent in new directions. Their journey resembles a person trying to escape an enormous crowd, while being pushed sideways or backward after almost every step. Because of this chaotic movement, energy may take around 170,000 years to cross the radiative zone. Beyond the radiative zone lies the convection zone. Here, the plasma is cool enough to become more opaque, so radiation can no longer carry energy efficiently. Instead, vast currents of plasma begin to move. Hot material rises toward the surface, releases part of its energy, cools slightly, and then sinks again. This continuous circulation creates patterns similar to boiling water, although the scale is almost impossible to imagine. The small, grain-like structures seen across the solar surface are called granules, and many of them are larger than entire countries on Earth. The visible layer of the Sun is known as the photosphere. It is not a solid surface that a spacecraft could land on, but a relatively thin region from which most visible sunlight escapes. Once light leaves the photosphere, its journey becomes much faster. After spending thousands of years moving through the solar interior, it takes only about 8 minutes and 20 seconds to cross the distance between the Sun and Earth. Above the photosphere are the chromosphere and the corona, the outer regions of the solar atmosphere. During a total solar eclipse, the corona can be seen as a pale, glowing crown extending far into space. Strangely, the corona can reach temperatures of more than 1,000,000 degrees. That makes it much hotter than the visible surface below. Scientists are still studying exactly how the sun's magnetic activity transfers so much energy into this distant outer atmosphere. Because the sun is made of moving plasma rather than solid material, different regions rotate at different speeds. This movement twists and stretches the sun's magnetic field. In some regions, the field becomes extremely concentrated, producing dark areas known as sunspots. Sunspots are not truly black, they only appear dark because they are cooler than the brighter material surrounding them. Around these active regions, magnetic energy can build until it is suddenly released. The result may be a solar flare, an intense burst of electromagnetic radiation that can reach Earth in only a few minutes. The sun can also launch enormous clouds of magnetized plasma into space. These events are known as coronal mass ejections, and some of them carry billions of tons of material away from the sun. Most solar eruptions miss Earth completely, but when one is directed toward our planet, it can disturb satellites, radio communication, navigation systems, and electrical networks. Fortunately, Earth is protected by its magnetic field and atmosphere. They redirect or absorb much of the dangerous material before it can reach the surface. Charged particles can still travel along Earth's magnetic field toward the polar regions. When they collide with gases high in the atmosphere, they create the northern and southern lights. The beautiful colors of an aurora are therefore connected to violent events on the sun. A display that looks calm and peaceful from the ground may have begun with an explosion powerful enough to throw solar material across millions of kilometers. Despite this danger, life on Earth depends almost entirely on the sunday. Its light allows plants to perform photosynthesis, forming the foundation of most food chains. Solar energy heats the land and oceans, drives atmospheric circulation, powers the water cycle, and influences nearly every climate system on our planet. Even much of the energy stored in coal, oil, and natural gas originally came from ancient organisms that captured sunlight millions of years ago. But the sun will not remain unchanged forever. It is currently a main sequence star, a relatively stable phase that has already lasted for billions of years. In about 5 billion years, the hydrogen in its core will become depleted. Fusion will begin moving into layers surrounding the core, causing the sun's outer regions to expand dramatically. The sun will transform into a red giant, growing large enough to consume Mercury and Venus. Earth may also be swallowed, although it will have become uninhabitable long before the sun reaches its maximum size. Eventually, the sun will release its outer layers into space, creating a glowing cloud of gas. The remaining core will become a white dwarf, a small and extremely dense object that will slowly cool for an almost unimaginable length of time. That distant future is not a threat humanity needs to face today. It is simply the natural ending of a star that has spent billions of years providing energy to an entire planetary system. Every forest, ocean, cloud, and living creature on Earth is connected to the sunday. Even the atoms inside our bodies exist on a planet whose history has been shaped by its light. The sun may look calm from a distance, but beneath its glowing surface lies a world of crushing pressure, nuclear reactions, powerful magnetic fields, and explosions larger than Earth. It is not an ordinary fire in the sky. It is a vast nuclear engine operating 150 million kilometers away. And every ray of light that reaches our planet is part of the energy that keeps our world alive.